Hi, this is Mrs. Davis. I am going to go over lesson 1.11, equivalent representation and the binomial theorem, looking at polynomials and rational functions. So, tackling our notes, we are going to talk about two forms first, the factored form of polynomials and the standard form, and then over here the factored form of rational and the general form of rational. Now there's good things about each form for each kind, for polynomials and for rational. So let's go through those and keep in mind, refresh yourselves, what are the pros and cons of each representation. So if you look at the factored form of a polynomial, you'll see that you can easily see the zeros, and you can see multiplicity, and then you can easily sketch the shape because you have the zeros and the multiplicity. So you can have the end behavior. Now that's not to say that the standard form won't give you the end behavior, but it's nice if you can sketch it out with the zeros. So on the standard form side, you can see the degree easily. It's not that you can't see it in the factored form, but it's sitting right here. You can see the y-intercept easily, because if you put zeros in for x, you would just get the 5. So there's two pros and cons. And so it's going to be something you need to do, is to be able to go back and forth between the two forms. Now let's go over here and look at rational functions. So the first example is factored form, and of course this is not crossed out yet. We should know that would be a whole, but if you're giving the factored form, give the real factored form before you simplify it. So if you look at this, you can easily see the domain. Okay, you can see the zeros. Domain would be from that. The zeros would be from the numerator. You can see any holes that might happen. And you can also look at the vertical asymptotes. So a lot in factored form for rational functions. And then general form, you can easily see the horizontal asymptotes, if there are any, and the y-intercept again. Okay, so that was just a very, very brief overview of the two pros and cons of the two forms of each of those functions. So let's look at example 1 to show you that it's good to be able to get back and forth. So if we have the first example, it's a polynomial and it's in standard form, and so let's pull off some of these things we can easily do. We have that it's a third degree because we look at the leading coefficient. If it's in standard form, these should be in order by degree from the highest down to the lowest. We would call this a trinomial because there's 3 terms. Hopefully you remember that. The end behavior. Okay, so now you have to go back and think, I have a cubic function, it's positive. And so that means that we know this must be the shape somewhat of the graph. So we can sit there and write out the end behavior. So we would write it in limit form. The limit as x approaches negative infinity of the function f of x is going to be, look down here, negative infinity. And the limit as x approaches positive infinity of f of x is equal to, up here, positive infinity. So that's how you're going to write end behavior, okay, in limit form. Now the y-intercept is very easy. If you put f of 0 in, you get 0. So our y-intercept would be 0, 0, and that, guys, is a point. Don't just tell me the y-intercept is 0. The y-intercept should be a point, so you need to get both the x and the y value. So of course the x value is 0 and the y value happens to be 0 for this one. Now the zeros, we'll have to do a little work. We're going to have to factor this to figure out the zeros. So if I take out a 2x, and then I have x squared minus 8x plus 16, that simplifies further to 2x, and then I get x minus 4 quantity squared. So I have two zeros, 0 and 4 has multiplicity 2. So we would write the answer for this as a set. X equals 0. We always make our sets least to greatest. And then 4 multiplicity 2. And if you're saying that, it's really nice to add the multiplicity, please, so that you can easily graph that. Now, when we want to know where f of x is greater than or equal to 0, we're going to get a better sketch because we now have these zeros. So I'm going to go over here and sketch this with the zeros. So if I have a 0 at 0 and I have a 0 at 4, remember the multiplicity means that if it's 2, if it's an even multiplicity, it doesn't go through the x axis. It just touches it and comes back the same direction. So it's a positive cubic, so it has to come here. It has to touch at 4 since it's multiplicity 2, and then it has to come around and come back up and go down through 0. So we don't have this maximum yet, but we don't need it to tell where f of x is greater than or equal to 0. So if you're looking at the function's negative here. Let's do it in red. It's negative here, it's positive here, and it's positive here. Now it asks when it is greater than or equal to 0. And so it's equal to 0 at 0, and it is going to be at a 4. It's still equal if it and then it goes to infinity. So the answer would be 0 to infinity, but now let me explain. If it was where f of x is greater than 0, you would have to split this up to be 0 to 4, because it's not greater than 0 at 4, it is 0 at 4. And 0 to 4, and then 4 to infinity. So that's just an aside, so just be careful when you're watching that. All right, I'll stop this video there and continue with the second one.